Picture this. It's April 16, 2026, and humanity just hit an absolutely incredible milestone in autonomous systems. You're sitting at mission control, but instead of typing out these complex, rigid lines of telemetry code to operate a satellite orbiting the Earth, you literally just type a plain English question into a chat box, and the satellite answers back. Welcome to this explainer where we're going to unpack the NAVI-Orbital mission. This was the very first in-orbit demonstration of a zero-shot vision language model, or VLM, performing autonomous multimodal inference right there on a low Earth orbit spacecraft. We're going to dive into exactly how AI agents are now successfully running in the extreme environment of space. It's truly fascinating stuff. So it all really starts with a fundamental question, right? How do you actually talk to a satellite? Well, for decades, the answer has been through highly specialized, hard-coded telemetry scripts. Operators essentially sent these rigid command sequences, telling the satellite exactly when and how to point its sensors. And then they waited. They waited to download massive stacks of raw data just to see if they got what they were actually looking for. But we are right in the middle of shifting to a groundbreaking new paradigm: language-driven edge reasoning. You're no longer predefining detection boundaries. Instead, you're asking an intelligent agent a question, and it's reasoning about the answer directly on the edge. It is a real game changer.
Here's our roadmap for today. 1. The orbital data bottleneck. 2. Meet NAVI-Orbital. 3. Orchestrating agents in space. 4. Hardware and edge constraints. And 5. The semantic compression era.
All right, let's jump right into part 1, the orbital data bottleneck.
You know, the primary flaw in current Earth observation is incredibly simple, but really frustrating. Data generation severely outpaces our downlink bandwidth capacity. We just collect way more than we can send back. With the legacy approach, onboard AI relied on these specialist detectors trained for very, very narrow pixel patterns. You acquire the image, you download massive, uncompressed raw pixel stacks to Earth, and if you want to look for something new, well, you face an incredibly slow cycle of retraining and software updates. It conflicts completely with mission agility. But looking at the NAVI-Orbital solution, we have semantic compression. Instead of raw pixels, you use a zero-shot VLM. Use prompt-based retasking to literally just tell the satellite what to look for, and it sends back concise, intelligent semantic text summaries. It completely inverts the old model.
Moving on to part 2. Meet NAVI-Orbital.
So the brain of the NAVI-Orbital spacecraft is a local Gemma 3 vision language model. And the absolutely critical capability to understand here is zero shot. This means the model processes live captures of previously unseen Earth imagery without any instrument-specific fine-tuning, none. It autonomously classifies scenes, produces text descriptions of the features it sees, and processes follow-up queries from the operator. It isn't just matching patterns it was explicitly taught to find, it's actively reasoning about what it's looking at, even when processing uncorrected YAM-9 instrument data right there on the satellite.
88.16%. That is the accuracy the zero-shot model achieved during ground validation against the highly curated 7,960 image AID benchmark. And you know, this wasn't just some fluke up in orbit. Rigorous flat-sat testing and ground benchmarking proved that these foundation models can operate on satellite-class edge computers without needing domain-specific retraining. I mean, that is an incredibly high baseline for a model that wasn't even fine-tuned for the specific flight instrument it was using.
All right, section 3, orchestrating agents in space.
To actually manage all of this, the engineering team turned to LangGraph. This is a runtime framework for building and managing long-running, stateful agents. Now, typically, you'd see LangGraph used for cloud-native LLM deployments safely down here on Earth, but NAVI-Orbital uses it as a graph-based state machine right on the satellite. So the crucial point here is that this framework basically acts as mission control inside the spacecraft itself. It coordinates dedicated agents for image detection and operator dialogue, ensuring really predictable state transitions without needing continuous ground intervention. Let's see how this all builds into an actual workflow, step by step. First, a plain English prompt is received from the ground operator. Second, LangGraph takes that natural language instruction, parses it, and routes the state to the appropriate agent. Third, the Gemma 3 model analyzes the live, uncorrected YAM-9 imagery based on that specific prompt. And finally, step 4, instead of gigabytes of clunky raw data, a lightweight, highly valuable semantic summary is transmitted back down to Earth. It's just a completely streamlined, language-driven loop.
Which brings us to part 4, hardware and edge constraints.
Now, when you're building for space edge AI, you have to remember that those cozy cloud-native safety nets just do not exist up there in low Earth orbit. For natural language prompting, developers have to program the system to handle ambiguous phrasing and fallback states completely autonomously. For multi-agent workflows, you literally have to map agent responsibilities to strictly deterministic state transitions, meaning if an error happens, the satellite needs an explicit hard-coded recovery path. And for hardware acceleration, developers must implement memory-aware batching and incredibly strict thermal throttling.
Expanding on that last point about hardware, the requirements here are totally unforgiving. You absolutely need optimized inference runtimes and memory-aware batching. You must have thermal throttling that explicitly matches the orbital duty cycles because, think about it, in the vacuum of space, dissipating heat from intense compute tasks is a massive, massive challenge. And finally, hardware-accelerated GPU inference. Running real-time vision language model inference within strict space power and mass budgets is completely impossible without it. It is absolutely non-negotiable.
Finally, Section 5, the semantic compression era.
This quote, directly from the original research paper, perfectly captures the true ethos and ultimate achievement of the NAVI-Orbital mission: to invert the conventional acquire, then downlink everything bandwidth profile through semantic compression of Earth observations in orbit. By prioritizing high-value imagery and text summaries over just hoarding raw data, we are officially entering an era where our satellites are no longer just passive cameras. They're active, reasoning observers. They process, they understand, and they compress vast amounts of visual data into actionable intelligence right at the edge.
So I want to leave you with this final, somewhat provocative thought to chew on. Are your edge AI architectures ready for the semantic compression era? NAVI-Orbital has proven, without a doubt, that zero-shot foundation models can thrive in the absolute most compute-constrained, extreme environments imaginable. The old, rigid paradigms, they're obsolete. As you look at your own development stacks, whether they're up in space or right down here on the ground, you have to ask yourself if you're still just moving raw data, or if you're truly ready to start moving intelligence. Thanks for joining me for this explainer, and keep innovating.